Welcome, everyone. I'm just so excited to see all of you. This is so great. I'm Hélène Langevin. I'm the director of the Osher Center for Integrative Medicine, which is jointly based at Harvard Medical School and Brigham and Women's Hospital. And it's just so wonderful to see so many of you here, and your presence here is really a testament to the strength and the size of the Integrative Medicine Network here in Boston. On behalf of the Osher Center team, I first want to express our gratitude to our sponsors, the Osher Foundation and the Weil Foundation, who sponsored this event, and also to Global Advances in Health and Medicine, who've generously provided a free 6-month subscription to all of the attendees, and who also have waived publication costs for all of the abstracts that were presented here. I also want to give a very special thanks to our fantastic program manager, Adra Nusrat, who has made this event happen. Where is she? I don't see her, but I'm sure she's around doing something important. So the Osher Center's new mission of connecting the Integrative Medicine Network, which is really embodied in today's event, began with its recent restructuring into a decentralized virtual center whose leaders in research and patient care and educations, who are Dr. Peter Wayne, Dr. Don Levy, Dr. Steve Schachter, Dr. Darshan Mehta, and myself, span several academic departments and institutions at Harvard Medical School. It is therefore my greatest pleasure and honor to begin this inaugural Integrative Medicine Research Forum by introducing the person who conceived of the vision of using the resources of the Osher Center to create a center without walls, Dr. David Golan. Dr. Golan is the Dean of Graduate Education, Special Advisor for Global Programs, and a George Minott Professor of Medicine at Harvard Medical School. He has been a steadfast champion of integrative medicine for many years and a key supporter of the Osher Center. And without Dr. Golan, it is fair to say we would not be here today. Thank you.
Well, thank you, Hélène, very much, and good afternoon to all of you. It's a real pleasure for me to be opening this inaugural Integrative Medicine Research Forum hosted by the Osher Center for Integrative Medicine at Harvard Medical School and Brigham and Women's Hospital. This research forum is a really exciting event for me and for many others who have followed the development of integrative medicine at Harvard. The vision for integrative medicine at Harvard, I think, really began with two pioneers whom we will be fortunate to hear from later today, Dr. Herb Benson and Dr. David Eisenberg. They can certainly speak for themselves, but I just wanted to say a few words about how the Osher Center for Integrative Medicine came to this auspicious moment. In 2001, the Osher Institute and the Division for Research and Education in Complementary and Integrative Medical Therapies were established at Harvard Medical School as the result of a generous gift from the Osher Foundation. The Institute and Division were founded and expertly led by David Eisenberg with the able assistance of Ted Kapchuk, Julie Buehring, Don Levy, Peter Wayne, and many others, some of whom are in attendance here today. In 2007, the Osher Foundation generously provided a second founding gift, this time to Brigham and Women's Hospital, to establish the Osher Clinical Center for Complementary and Integrative Medical Therapies. This center has been enthusiastically led for the past 7 years by Dr. Don Levy, who is known far and wide in the integrative medicine community as the practitioner's practitioner. Just 2 years ago, these two terrific entities came together with a new vision to form the Osher Center for Integrative Medicine at HMS and BWH, and a national search found the perfect director in Hélène Langevin. The new Osher Center is indeed a center without walls, with a mission to form strong links for researchers, educators, and practitioners in integrative medicine throughout Harvard Medical School, Harvard University, and the HMS-affiliated teaching hospitals and research institutes. The new mission extends to the other Osher centers as well, initially at UCSF and the Karolinska Institute, and recently at Northwestern and Vanderbilt as well. Helene has embraced this vision with passion and is now implementing it at a furious pace. She's rapidly building and consolidating our integrative medicine community and is developing educational research and clinical programs across the spectrum of biomedical science and medicine relevant to the diagnostics, therapeutics, and prevention in integrative medicine. It has been a personal pleasure for me to serve on the Osher Center Oversight Committee, which has allowed me to see this incredible progress firsthand. In closing, please allow me to express what a great pleasure it is for me to see all of you here today, the Harvard-wide community in integrative medicine. Represented here today are basic translational and clinical scientists, clinicians, and teachers across the spectrum of integrative medicine. Heartiest congratulations to Helene and to all of you for making this exciting event happen. I'm sure it's only the first of many such events to come. Thank you.
Oh my, thank you so much, David. I am now delighted to introduce one of the true pioneers in the field of integrative medicine, Dr. Herbert Benson. Dr. Benson is the Director Emeritus of the Benson Henry Institute for Mind-Body Medicine and Professor of Medicine at Harvard Medical School. It's important to remember that the mind-body connection that is so central to many of the topics that we will discuss here today was not so obvious just a few decades ago. Dr. Benson's work on the relaxation response was one of the first to quantify the physiological interactions between the mind and the body, and that we now take for granted. The growing collaboration between the Benson Henry Institute and the Osher Center has been an important catalyst in making the idea of the center without walls become a reality. Dr. Benson.
Good afternoon. What I'll speak to today will be a personal perspective of what's happened over the last 40 plus years. 150 years ago, there was no medicine other than integrative medicine because scientific medicine had not yet evolved. But starting with Louis Pasteur in France, defining a cause of anthrax, with Robert Koch in Germany, describing the isolation of bacteria. In Canada, Banting and Best came up with insulin, which could then treat diabetes. In the United Kingdom, Alexander Fleming discovered penicillin, and pneumonia became treatable for the first time. Pneumonia prior to that was a lethal disease, with well over 50% of people suffering from pneumonia dying. This then became treatable. Then at Merck Sharp and Dohme, scientist Waxman came up with came up with streptomycin, which made tuberculosis, the White Death, treatable. And by biblical standards, miracles were being produced routinely. People could see again, blind people who had cataracts. And what occurred was tracing this evolution was the Flexner Report in 1910, brought about by the Carnegie Foundation, essentially saying that scientific medicine, evidence-based medicine, was essential. And in that context, because mind-body interactions, stress reactions, were not easily quantified, they went off to the side a bit and actually became ridiculed. But here in Boston at Harvard, there were periodic reinfusions of, hey, there's something else going on here. Oliver Wendell Holmes starting that, pointing out the importance of the doctor-patient relationship. William James, the mind cure movement was started by him, both graduates of Harvard Medical School. And then Walter B. Cannon described the fight or flight response in the 1920s and 30s. And I had the good fortune of working in a laboratory in the early 1970s, which were studying the opposite of the fight or flight response, which became defined as the relaxation response. And even in those days, as was just pointed out, the bias against mind-body medicine was so powerful that when I received a grant for $300,000 in the early 70s, now equivalent to $1.5 million, Harvard Medical School questioned the wisdom of taking such a grant because considering mind and body in this type of integrative medicine was not acceptable. So I went to the dean of the Harvard Medical School, Robert Ebert, asking his advice. And his conclusion was, if Harvard can't take an occasional chance, who can? Take the money. And then with that, we were able to find other support along the way. For example, one of the earliest people recognizing this worth was David Rosenthal, who, as head of Harvard University Health Services, invited me to lecture at the law school, at the business school, at Arts and Sciences, introducing this work. And then John Henry, believing in this work, made a sizable donation of close to $20 million, and hence the Benson Henry Institute was founded at the Massachusetts General Hospital. And throughout, the support came because we were adhering to the evidence-based reductionistic model which constitutes science as we know it today. And the support for all of these came from numerous people, just several of whom I would support and I would mention now. For example, 10 or so years ago, working with Tuvia Lieberman and Manoj Basin, we were able to define the genomics of the relaxation response, namely a set of genomic interactions which led to decreased inflammation, to less energy metabolism, to insulin secretion, and to telomere length. And throughout, the support grew and grew, and we were thrilled with the founding of the Osher Institute and look forward to its collaboration. But the work we are now doing transcends simply the scientific clinical applications of this. For example, if integrative medicine, evidence-based integrative medicine as we know it, is going to be integrated into everyday life, the population has to be changed. And so the work, the educational initiative of our institute under Marilyn Wilshire is now bringing this to children from kindergarten right out through college. We have, and working with people at the Osher Institute. We're trying to bring this internationally, for under the superb leadership, without whom I wouldn't be here, Dr. Greg Fersone is bringing this care, the caregiver, integrative medicine, to people treating Ebola patients. We're also working, for example, with the military, with a NICO to treat PTSD. And so what I see is what began really many, many centuries ago as integration was lost because of the justifiable rise of modern scientific medicine, now returning with a scientific base. So I am thrilled to be here today to watch this evolution as it is today and look forward to a prosperous, successful future that will help the health and well-being of all people. Thank you.
Thank you so much, Dr. Benson, for giving us this wonderful perspective. I first want to take a few minutes to reflect on what we mean when we talk about integrative medicine. The term integrative medicine is relatively new, and it came about in an effort to sort of join together conventional and what we call alternative medicine or complementary medicine, or affectionately CAM. At the moment, research in integrative medicine mostly aims at testing the efficacy and the mechanism of these CAM therapies or practices, like, for example, acupuncture or meditation. But it is also useful to think of integrative medicine in a broader sense. Oops. Broader sense, sorry. Which is to arrive at a fundamentally deeper understanding of the human body and health that underlies both conventional and alternative medicine. Conventional medicine suffers from being compartmentalized, from the long-standing physiological separation between systems and body parts. Many alternative practices, however, have a holistic view of health and disease that has begun to dissolve these artificial boundaries. This view of integrative medicine has a lot in common with other like-minded integrative disciplines within medicine, such as systems biology, for example. What is unique about integrative medicine research, however, is that it derives its concepts and hypotheses from healing traditions that are outside of what typically is taught in medical schools and in basic biomedical science education programs. Making more and more connections between integrative medicine and other like-minded disciplines, like systems biology and across traditional organ-based biology, will contribute to an ever-expanding understanding of human health and disease that will apply to all of medicine. This expanded understanding at a basic level, at the physiological level, is essential to the full implementation of integrative medicine into medical education and patient care. Now, Boston is a truly unique environment for integrative medicine, as it contains multiple integrative medicine centers within several institutions, many of which are represented in today's program. However, the sheer size and complexity of Boston, and particularly Harvard Medical School, can be an obstacle to working together and can result in groups of people operating in a vacuum. In other words, integrative medicine is not as integrated as it could be. One of the main goals of the Osher Center is to help connect the large number of individuals and centers that do integrative medicine research, education, and patient care, but that may not yet be collaborating or may not even be aware of each other. At the Osher Center, we decided to build a map to see how connected this network may be. Each dot on this map represents a person, an individual that has published at least one paper on a topic related to integrative medicine. This map identified an impressive 670 researchers connected to 19 institutions, including Mass General, Brigham and Women's, Dana-Farber, Children's, and BIDMC, and many other institutions. And you will be hearing more about this map from David King, who's the CEO of Exactive, who built this map for us. Hopefully, most of you have already seen this network map on our website and had the opportunity to navigate it on your own. In the map, people are linked to each other via publications that they have published together, and are also linked to their parent institution. The map clearly shows that an impressive amount of connections exist between people, and through these people, between institutions. Today's meeting is a physical embodiment of this network map, and it's wonderful to see how many of you are here today. The goal of this forum is first and foremost to get to know one another. We hope that some of you will find new colleagues with common interests and new opportunities for collaborating, sharing, and leveraging of resources. You will hear presentations by leaders of 9 different integrative medicine centers and programs, 7 at Harvard Medical Schools and 2 at neighboring institutions, Tufts and Boston Medical Center. We are painfully aware that there are many other integrative medicine research groups that we were unable to include in this program due to lack of time in this very short half-day event. However, we hope that this forum will be the first of many, and that future more extensive events will allow even more voices to be heard. We understand from our survey that many of you are interested in education and patient care. Although this inaugural forum is primarily focused on research, an important future goal of the Osher Center is to represent existing educational and clinical networks, as we have done for research. Input from this forum will be an important first step in this direction. What will happen as a result of us meeting today? Will the network change as it becomes aware of itself and of us having gathered here for the first time? How might we want to influence the growth of this network? Will becoming a conscious network give us more collective strength and visibility as a group? Our keynote speaker, Dr. Albert Laszlo Barabasi, is an expert in networks, and he will talk about the science of networks and what we can learn from measuring them and understanding their behavior. Dr. Barabasi is the Robert Gray Dodge Professor of Network Science and a distinguished university professor at Northeastern University, where he directs the Center for Complex Network Research. He holds appointments in the Department of Medicine at Harvard Medical School and Brigham and Women's Hospital in the Channing Division of Network Science, and is also a member of the Center for Cancer Systems Biology at Dana-Farber Cancer Institute. Dr. Barabasi's work led to the discovery of scale-free networks in 1999, explaining their widespread emergence in technological systems from the cell phone to the World Wide Web. Dr. Barabasi.
Thank you. I will use this one here. Oh. I have no choice. All right, let's see the technology. We can make the technology work. Let's see. Could I get that on my screen up? View presented. Yeah, perfect. Okay. So, hello everyone, and thanks for the opportunity of being here, and normally when I come to this room, I talk about network medicine, and this time I was told that I should just talk about networks in general, which I just as much pleasure to do. Indeed, I'm by training a physicist. Today I define myself as a network scientist. And in my lab we study a bunch of things. We study networks like the internet, how the routers connect to each other, different computers link to each other by physical links. But at the same time we study the protein interaction networks behind the human cell. and how those interaction networks hide kind of the cause of disease and how we think about diseases from a network perspective. And we're not shy to look at social networks either, like the Facebook map that you see over here, where the nodes are individuals and links represent the linkages among us. And try to extract from these maps what are the underlying organizing principles of these systems. And these are very different systems from each other. One has nodes, computers, the other one has molecules, the third one actually is individuals. And the fundamental challenge for us scientifically is how do we think about these very different type of networks? Are these really each of them belonging to their own discipline, having no common principles? Or maybe there are common principles, and how do we quantify that and can really inform our understanding of the complex world behind us? So that's really the fundamental question, and whenever you start studying any network, whether social, biological, or computer, or you name it, the question is, how do we really describe them? How do we kind of quantify them? How do we speak about them? What's the language of networks? And some of the early work in this direction came from the work of two Hungarian mathematicians, Paul Erdős and Alfred Rényi, who in the 1960s, they said, well, networks are fundamentally simple from a scientist's perspective. They're just nodes and links. So the challenge for us mathematicians, however, is that we don't know how nature decides to put the links between the nodes. So that's what we really have to figure out. And they look big and messy and complicated and random, so therefore let's assume that they are random. And let's assume that these nodes are completely randomly connected to each other. This means that you would pick each pair of nodes and you throw a dice, and if you get a 6, you put a link between them. If you don't get a 6, you don't connect them. In other words, you let randomness to drive the underlying structure of the network. And if you do that for this tiny network, this is what you would get. And some nodes will be connected, others will not. Some will be lucky and connecting many links. Some will be less lucky, having only one link. Now, this is, of course, a toy. I'm showing you only a few nodes. The question is, what happens if I do that not for a few, but for many, many nodes? And I don't just use the dice, but I let the probability to change by which I connect the nodes. And that's what's kind of shown in this video, where at the beginning, all nodes are disconnected, and I'm going to increase the probability of connecting the nodes by throwing new and new links between them. So first we have a bunch of isolated nodes, and what the links do is they start forming pairs, friends who know each other and so on. And what you realize is that as I'm putting more and more links, these pairs will join up into these pathways, if you want to call them that way. And eventually, once the probability reaches a certain critical point, and this is really the biggest discovery of Erdős and Rényi, these nodes suddenly join each other, and something that we would recognize as a network will form. So what they really showed in 1960 is that the emergence of a network is not a gradual process, meaning that if you have just a bit of more links, you're not going to have a bit of more network. What you have is that for a wide range of connectivities, you don't have a network. In order to have a network, you have to reach a critical point, a critical number of connectedness, and suddenly, more like a phase transition phenomena in very fast, the network emerges. So this was really kind of the status in the 1960s, and what we'd like to focus on one particular property of this network, which is how many links each node has. This is what we call in this network science the degree of a node. This node has degree 1, this has degree 4, and if you want to look at the large network, what Erdős and Rényi have shown is that the degree distribution, that is a number of nodes with a certain number of links, follows a Poisson distribution. What does that mean? Well, a Poisson distribution means that we have a typical number of links per node, and because the Poisson decays very fast as you get away from the average, it also means that there are really no outliers. There are no highly connected nodes, or no one is left behind. That is, if the society would be random, that we would randomly make friends, and to a certain degree we do, but if that would be a truly random process, then most of us would have approximately the same number of friends. There would be no highly popular individual, and no one would be really left behind. So to kind of get a visual sense of it, a Poisson distribution looks like that on the top left. And visually, a network with a Poisson degree distribution looks a bit like the highway system of US, where the nodes are the cities and links are the highways, because most cities have 1 or 2 highways kind of going in and out. You don't have a city with 500 highways going in and out. So it's a relatively uniform, kind of boring network if you look at that perspective. One of our kind of probably more important discovery in the 99 that was kind of referred to in the introduction was that there is really no network like this out there. And just about anything that I told you so far, random networks, is beautiful mathematically, but has no connection whatsoever to reality. Real networks are not random. And one of the first hints that we got that they are not random is when we looked at how many links each node has, first on the World Wide Web and then on many other networks. And what we found instead is that the degree distribution follows what we call a power law distribution. You don't have to know much about the power laws per se, but what it really shows the power law is that we have a bunch of nodes with a few degrees, that of small, very not too connected nodes, and they coexist with a few very highly connected nodes that we will name them hubs from now on. Visually, a network with a power law degree distribution looks a bit more like the airline system of the United States, where you have many, many small airports and a few major hubs that hold these networks together. These networks today are called scale-free networks, kind of reflecting the fact that in a random network, a typical node, the average degree is very typical. That's the scale of the system. In this network, there is no node you can pick and say, this is just like everybody else, because many small nodes coexist with a few very, very large nodes. So that was a mathematical discovery that the distribution is different. The question is that something peculiar to 1 or 2 networks like the airline system, or rather it's a generic property of many other networks? So let me show you some examples. So this is the internet. This is a physical network where the computers are connected by cables. So it's not the World Wide Web, it's really the infrastructure behind our communication system. And you can see a few major hubs holding many, many peripheral nodes. And indeed, in 1999, a famous paper by Faloutsos, and Faloutsos, they measured the degree distribution of that and finding that this is actually a scale-free network. So that's technological networks. How about social networks? Let me give an example that I'm going to use a few times in this presentation. What you see here are the members of a company, that are the workers or the employees of a company in Hungary. And these employees work in 3 different locations. The purple guys work at the headquarters, and the blue and the kind of yellow-greenish work at 2 off-site locations, the manufacturing sites. And the reason we know about this is because this particular company turned to us being a company that I founded a few years ago in Hungary, that they have a communication problem. What does it mean, a communication problem? They realize that every time the upper management and the CEO makes a decision where the company should be doing and what is the next direction, that news is not getting to the employees. Sounds familiar? Not only that is not getting to the employees, but often the opposite news is traveling among the employees. And they ended up hiring an HR firm who really confirmed that that's right, that really what the employees talk about has nothing to do with what the management thinks about, where the company is heading. So they asked us if we could figure out what's happening within this organization. Where is the breakdown in communication? Now, getting a list of employees is really not particularly helpful to figure out what's happening with the organization. We need to know where information is spreading. So we actually deployed an online service that we have for this purpose, where everybody was asked, tell me 4 or 5 people you talk on a regular basis about job-related issues. Where do you get your assignment? Where do you delegate your assignment? So that is, where does power and information is flowing within the network? And this list kind of became a map. And what you see now is that suddenly we have employees that look like hubs. And I want to emphasize these are not hubs because they think very highly of themselves. They are hubs because lots of other people pointed to them as being the source of information about company matters within the organization. We'll come back to this example because obviously many of you are thinking, who are those guys? And what's the problem that the company has? So we'll return to that towards the end of the talk. But what I just wanted to show here is that these hubs are present in the organizations, in all organizations that we are part of. And of course, they are present in this particular organization. Now, if you look from that perspective, you can clearly see the hubs over here. Now, of course, this is what we call a bipartite network, that the institutions show up as hubs, but I'm sure if you would do the node level map, you would see exactly the same behavior, and maybe we're going to see it in the coming presentation. And the final example I want to give is, comes from a completely different domain. All the networks I showed you so far were created by us. That is, they're human creations. Let's find a network that we did not consciously build, because maybe hubs are something that we do, and maybe let's find a network where we didn't do. And that's the networks within our cells. So on the left-hand side, you see a depiction of the metabolic network. Obviously, you know what it is. That's the network that kind of works on the burger that you may have during lunch and turns into something that your cells can recognize, like ATP and ADP. And on the right-hand side, you see a protein interaction network where the nodes are proteins and the links correspond to binding interactions between them, as discovered by different yeast to hybrid techniques. And these are for yeast, but we have similar maps for humans as well. And if you look at, for example, on the right-hand side, you see that there are a few major hubs that hold many peripheral nodes together. And indeed, the analysis of this network and of all other organisms' networks turn out that both the metabolic and the protein interaction network are scale-free, that they have these hubs. And as I said, this is not only for yeast, but a few years ago, Mark Vidal's lab here at Dana-Farber discovered that humans have exactly the same underlying architecture, human cells, which is pretty amazing if you think about it. Because the internet has a history of 50 years, airline systems, something like that, social networks, whatever. This has a 4 billion year history. And what we are finding, really, that the underlying architecture and the mathematical structure of these networks that have apparently nothing to do with each other is the same. Almost, if you want to be metaphysical, as if the same creator would have built them, which scientifically raises a fundamental question. How is this possible? How is it possible that the World Wide Web, the internet, and the cell over 4 billion years converge to the same underlying structure? And what's wrong with the random network model that is not telling us about hubs? So to answer that, let's go back and really ask the question, what did go wrong in that model that I showed you earlier? Why are we missing the hubs there? And it turns out that that random network model has two hidden assumptions in there that really don't stand up when we look at real networks. The first assumption is that we assume that the way we model random networks is that we first have a bunch of nodes, and then we somehow cleverly connect them, in this case using a dice. In there is the assumption that while I'm connecting the nodes, the number of nodes don't change. In reality, networks always change. They always expand through the addition of new nodes. All the networks that we see out there are the result of some kind of growth process, some kind of evolutionary process. You don't pop up with 1 billion nodes right away. So this means that, think about, for example, the World Wide Web. 20 years ago, we had only one web page, Tim Berners-Lee's famous web page in Geneva, and now we have more than 1 trillion. How do we go from 1 to 1 trillion? One node at a time. So that means that if you really want to model a network, you shouldn't just put down a bunch of nodes and connect them, but you should mimic the process by which they came into being. That is, you start from a small network and you add nodes to it. One, yet another one, yet another one, kind of what exactly really happened generally in the real networks or in this particular network that you are part of here. Now, when you do that, the new node has to make a decision where to connect, what other individuals will seek out. And Erdős and Rainier, the random network models, gave us the recipe that happens completely randomly. And again, that's not true. And the way it's not true is that instead of connecting randomly, new nodes have a preference towards connecting towards the more connected nodes. And again, the web is a good example to think about it. How many web pages do you know personally? A few hundred at most. What is that you know? You know Google, Yahoo, and the big nodes, HMS, and so on. So we tend to know the more connected pages, and we connect to what we know. So we tend to be biased in our connection patterns towards the more connected nodes. The bigger nodes are easier to find in any network. This is what we call preferential attachment. And preferential attachment simply says you can connect to any node you want, but you are biased. You are linearly biased towards the more connected nodes simply because they're easier to find. And if you put these two ingredients together, growth and preferential attachment, you will get a network that will naturally grow hubs. And it would do so through a rich gets richer process, because if you have two nodes in the network, one is big and one is small, when the new nodes come in, they're much more likely to find the big node than the smaller one and connect to it, and therefore the big node will continue growing faster than the small one and will eventually turn into a hub. So, and if you kind of go ahead and simulate this, you will find that this will be a network that has a power law degree distribution. As I showed you, it will be a scale-free network. So what is it we just did here? We said there are two very simple ingredients, growth and preferential attachment. And if those are there, you will have hubs. You will have scale-free networks. There's lots of other stuff going on in networks. Nodes can drop out. Links can drop out. Nodes can rewire themselves. But as long as the network continues to grow, and as long as there is some degree of preferential attachment, the hubs will develop and persist in the system. And because there are only such a little needed for that, that's why so different systems develop the same underlying architecture. They all grow, and it turns out that all of them actually have some degree of preferential attachment for various reasons. So now we know how important the network's evolution and the growth is, which is probably something to keep in mind for your organization as well. If you stop growing, your network will fundamentally change. Now the question you might ask next, so what? Why do we care about these hubs? And the reason we care about these hubs is because once we have them, they fundamentally change the behavior of a system. And let me give you one example. Talk about robustness. How robust is a network, an organization, to the removal of neat nodes, of people leaving? Well, how do we model that? Well, one way to model it is start from a network and remove a couple of nodes. These are employees who left. These are genes that broken down, or proteins that are not functional. And the question we want to ask, what happens to the network? And if the right nodes are missing, and the right number of them, the network will break into pieces, as I'm showing you over here. This problem has been much studied in the 1960s under the name of percolation theory. And the answer is very simple. If you have a random network or a regular network, like a square lattice, and if you randomly remove nodes, if you just remove a few, it doesn't matter, because the remaining nodes will find ways of communicating with each other. But each network has a threshold. And as you approach that threshold, eventually the network will break apart. In other words, you don't have to remove all the nodes to destroy the network. It's sufficient to approach that threshold, and the network will inevitably break into tiny pieces, become non-functional. That is true for random networks. It's true for regular networks. It's not true for scale-free networks. Let me show you why. So we start from the network that we built earlier, and I'm randomly removing the nodes, and you will see the network is shrinking but not falling apart. And the reason of that is because I have only a few major hubs and many, many small nodes. And if I randomly pick my nodes, and which failure is random breakdown, then mostly the small nodes will be disappearing. The big nodes will get smaller and smaller. Your chance of hitting a hub is very low, but even if you occasionally do, not the end of the world, because there will be some other nodes who can take up the responsibility. But down the line, the network will actually survive that. So effectively, what we learned is that networks, because of the hubs, are very, very, very robust to random failures, but there is a price you pay for that. What if I don't remove the nodes randomly? What if instead of going randomly, I'm going to go for the hubs, that is, attack the system? And that's what I'm showing you in the next slide, is that I'm removing the biggest slide, the next biggest slide, and yet the next biggest slide. And what you see is that on the left-hand side earlier, I removed about 25 nodes. Now I'm showing you 7, and the network broke into tiny pieces. Here, well, the network was intact. Here, however, removal of a few nodes already destroys the network. So this is what we call the Achilles heel of these real networks. They are very robust to random failures, but they're extremely fragile to attacks. That is, if you protect your hubs, the network will stay in place. If, however, a mechanism destroys the hubs, the network is very sensitive to the missing of the hubs. Now, hubs play an important role in another process that is just as important, which is spreading phenomena. I heard references to the Ebola outbreak earlier, And that's, of course, one of the typical network-based problems. A disease is spreading from individual to individual on the contact network. And this is actually an area where my institution works a lot. In our Network Science Institute, we have Alessandro Vespignani, who is the WHO's official modeler. He's the person telling us how many people will get sick next week or 2 months from now, both in Africa, as well as how many patients we expect to arrive to the US and other countries. Now, when it comes to epidemiology, there is a fundamental dogma that is well understood by epidemiologists, is that if you look at what fraction of the population is sick at a given moment in function of the spreading rate of the virus, if the disease is not spreading too easily, that is hard to pass it on, then effectively will die out in the population. And because you get cured before you could pass it on to someone. However, once the spreading rate reaches a certain point, then the disease will become endemic and a certain fraction of the population will always have it. And of course, this is the diagram based on which we protect ourselves from viruses. This is why we take flu shots. Partly the flu shots protect us, but partly the flu shots decrease the spreading rate, and the hope is that we'll put the disease under the threshold and will naturally die out. This is why we're told to use condoms. Partly protect us, but also slows down the spreading process of the disease, so puts it under the threshold. Turns out this picture that has been really the bedrock of epidemics is true for random networks. It's not true if you have hubs. If you have hubs, your critical threshold disappears, and your curve will become like that orange one over there, which means that even very weakly virulent viruses can spread. How do they do so? Well, the hubs are always the first to get infected because they're in contact with so many individuals. Once they get infected, they broadcast the disease to other hubs and to many other individuals. So the disease will persist in a group of hubs who will continue spreading to other people. And this recognition, as well as understanding the underlying contact networks, has really brought a revolution if you think about spreading processes. And that really, what you see here is the 2009 epidemic of H1N1, which was in May 2009, was fully predicted how many people will get sick in every city around the world for the coming months, and made a couple of incredible predictions telling us that the disease will peak out in November, not in January, as typically influenza-type viruses will peak out. And they told us that the vaccine, when it will arrive at the end of November, will be too late. And these were very heretic predictions back then, but they turned out to be right. And this is the methodology, this network-based methodology that today is being used, for example, for Ebola, based on which we're told how many individuals will actually be infected tomorrow. So why am I telling that? Because all of this works thanks to the understanding the underlying network, and the epidemic threshold disappears because of the hubs. So that's another reason why hubs are so important in these underlying networks, not only for robustness. Let me very briefly switch gears and go into the subcellular world. I like to show this one to non-medical audience. Of course, for a medical audience, the answer is always very obvious. This is a simple molecule you get into your body, binds to COX-2, and does lots of good things for you. And the question often what I ask is, what is this molecule that has so many good benefits? And of course, most of you know the answer is aspirin. But the question is, how is it possible that one molecule can have so many different effects in the cell? And the reason has to do with the underlying network. Because when you actually learn biology, when I learned biology, we were told a lot about the architecture of the cell. We were told about the nucleus, the cell wall, and many other organelles. But what I would like to argue today is that knowing this information is very important, but just as useful for understanding how the cell works as looking at the back of my watch. People would say, oh, you got a battery, and you got a condenser and many other components. These are the structure elements. But we all know that the reason why my digital watch works is because there is a wiring diagram behind the chip. And that's the one that really makes it click. And if you want to understand, that's what you have to look at. In the same way, if we want to understand how the cell works, we're going to have to decipher the underlying wiring diagram of the cell. And when I came to Harvard Medical School about 7 years ago, first as on a sabbatical, we started first asking, how do we think about the disease and the gene dichotomy, where most people tend to think when they see that a new gene has been discovered for a disease that there is a one disease, one gene relationship, and we know that's not the case. Rather, the same genes can be involved in many diseases, and the same diseases can be caused by many genes. If you kind of try to reflect that, you will end up with what I call the disease network, whose nodes are diseases. Size of the node corresponds to how many different genes correspond to that particular disease. And links to diseases are connected if the same gene is involved in both of them. Why would you do that? Because it reflects the fact that they have common genetic origins. And when you look at this map, the first thing at least that comes to my mind is that how diseases that are fundamentally different, and the different kind of diseases are shown by different color here. Red are neurological diseases, blue, these bluish things are cancers. How completely different diseases whose treatment happens not only in the different floor and different doctor, but often in different hospitals, are really connected at the cellular level. So there is one underlying reality, which is the underlying network where everything is happening, and in many ways, the way we classify diseases is a bit of construct of the best we could get back then. And so what I'm trying to say here is really that if we want to understand diseases, we have to look at fundamentally at the network level. But what is a disease in this network? And to understand that, I'm going to really kind of give you one more example, one important property of networks, which is the existence of communities, which is important for this community as well. What you see here is a mobile phone network, who is calling home in a large country. This is a small portion of that. And of course, it's a hairball. It's completely impossible to see anything in that. And if I would show you the full one with 4 million users, it would be impossible to see anything. Yet, we have lots of tools by which we can go into the network and find communities. Communities are groups of nodes that tend to work together more often than you would expect by chance. People who talk to each other regularly. And these are a couple of communities that you see inside the network. I found them only based on the network topology. I'm not using any auxiliary information. The question is, are these communities meaningful? Do they really do something similar? And to show that, I'm going to show you here now 2 snapshots of this network where I'm giving you one piece of additional information that I didn't use earlier. How often they call each other at noon or at midnight, these individuals. So this is the same community at midnight, at noon. And what you realize if you look at it is that that particular community on the right is very busy at midnight and sleeping at noon. And the next community is the opposite. It is actually very busy at noon and sleeping at midnight. What this one shows is that the topologically connected structures are similar to each other. They have common activities. And the reason I'm showing you is not only because this is part of our activity, our community as well. I'm sure your community has many modules like that. But I'm showing you because this is the way we think about diseases as well. In the cell, there are modules that are responsible for certain functions. These are group of molecules that interact with each other, react with each other to carry certain function. You mess with that module, you break that, and you get a disease. There are many different ways you can break a module down, and you will get the same phenotype. That's why so many different genes can lead to the same disease. And today, this is how it looks like. What I'm showing you is actually asthma. That is where the asthma genes are in the cell, and you can see that they're in the same neighborhood. And knowing that, we can actually discover what we call the asthma module, which is really where asthma is residing in the cell. And we can do that not only for asthma, but for many other diseases. So this is kind of taking us a step closer. How do we think about human diseases? They are really defined as communities or neighborhoods in that network. And for each disease, we have to discover a different one. So I think I'm slowly running out of the time. I promised at the end that I'll tell you a little bit the resolution to this particular problem, which also has to do a bit with communities. So you remember, these are the employees of the Hungarian company. And once we actually mapped out their communication pattern, it turned out that there were a couple of major hubs in the system. And the question is, of course, who are these guys? And what should we do with them? So the first instinct you would have is that, of course, we should have hubs because there are important people in the network, and they should be very connected. So therefore, we would guess that the people who are hubs are those whom we think are important, which is the leadership. So let's put the leadership on the map. So the CEO and the board of directors are shown in red, and unfortunately, there is no hub among them. The next level is the top management, which are blue nodes. And I don't know, I can see, you probably cannot see any blue node over there among the hubs. The first hub you actually see among the next level, which is just ordinary management. And the biggest hub in the center of the network really comes from the bottom of the organization, which here we benevolently call them associates, which is a nice way to say ordinary employees. And indeed, that guy in the middle, he's in contact with everybody, almost everyone in the organization. You see, he has links for all three parts of the company. So he connects to just about everyone except the higher management. So the question is really, who is he? And of course, we know the answer. And he is the person who is in charge of health and safety within the company. So his task is to go from group to group and talk to everyone and see how they're doing. He's a very outgoing person. He's a very talkative fellow. So he learned to pick up information here and pass it out over there. He became the gossip center of the organization. Unfortunately, the way he's located, he has no access to authentic information. So then the question is, what do we do with him? And I typically, in a smaller group, if I ask this question, I get three answers. 1, fire him. 2, promote him. And the 3, which is probably, you guessed the right answer, just tell him what's going on. And tell him and a few other individuals, organizations, and this is what networks really give you. It gives you a dashboard of what's really happening within an organization, whether that's a community like you guys, or whether it's a company like Harvard, or whether it's a company, or whether it's a hospital like Harvard Medical School Education Institution. We really have no way of looking into these organizations and understanding their inner function unless we start mapping out their networks. And this is kind of like the message that I was hoping to convey to you. Looking through networks really opens up new avenues from the subcellular work to think about diseases and drugs, all the way to understanding the world which we are a part of, the social network and technological, and we live in the age of the network. Kind of not having those network glasses will really significantly limit our vision. Thank you very much for your attention.
Thank you so much, Dr. Barbasi. That was a real treat. And we will follow with one more treat, which is our next speaker, Mr. David King, who is the founder and CEO of Exactive. And Exactive is a company that specializes in producing data visualization tools to facilitate the cross-fertilization of ideas and innovation. And it created our web-based integrative medicine map that you just saw. If a picture is worth 1,000 words, then I think an interactive map is worth 1,000 pictures. And so I will let David take it away. Thank you.
Well, thanks for having me, and it was great to get all of these great examples from Dr. Barbasi, where we saw networks that were comprised of so many different things. We saw networks that were comprised of people, networks that were comprised of atoms, networks that were comprised of genes. And once we get my slides up, I'll tell you about the sorts of networks that I'm particularly interested in. Harvard Conference. Yep, that's it. At one point, when Dr. Barbasi was talking, he said, okay, so this is how networks behave, so what? So what then, right? And it's showing up here, but not there. And I think that's a really important question. That's the question I kind of want to use my talk to pull us back to. We understand these amazing phenomena. We see the math behind the networks. We see how they behave. And we're even now aware that we're all part of one of the integrative medicine community. So what? What does that mean for us? And it's funny, it's just after Halloween. It's kind of a Halloween title. There are people in the dots. This is what I get really excited about, is that while there's networks for all sorts of different things, And almost all the times when you see these sorts of network talks, you see a lot of dots and arrows. And we even talk about, in our lexicon, we talk about connecting the dots. But one of the things I want to spend today talking about is that there are people in those dots and what happens when you connect those. So out of curiosity, how many of you have had a chance to play with the interactive network visualization? Oh, that's great. That's great. We'll play this. This is the green is going to be hard to see, but pretty quickly we're going to bring in other topics like Tai Chi. Okay, so us network guys, we like to have these networks that float around with these sort of forces. And this is available on the web that you can play with it, and it's also available outside. And I'm going to encourage you to try it out when you take a break. So this is what one portion of what my company does. We use technology to build tools that allow us to visualize data. And when we visualize data, we sometimes do that. I think data visualization happens for one of two different reasons. One is to try and find some discovery in the data, so exploring it. But then once you've found something, you also have to be able to communicate it. I think those are two very different reasons for data visualization. And I think part of Elaine's real vision in what she's done with Osher is recognizing that there is a lot of power when you can communicate to the group what's going on behind the data, which in this case are all publications and co-authorship and institutions. So as the CEO of a company that makes a large portion of our revenue from data visualization, I'm going to tell you a secret that you can't tell anybody, which is I don't really care about data visualization. What I care about is I care about innovation and how we can use technology to facilitate innovation. I care about human creativity. And I happen to think that data visualization is a very interesting way to facilitate innovation. But for me, what I'm very excited about really in the technology, in our growing understanding of networks, is innovation. And when I look at this network, that's what gets me excited, is that this is a large group of people that are all doing cutting-edge work in different areas. How can we use our technology? How can we use our understandings of the math and the dynamics that Dr. Barabazi talked about? How can we use that to connect the people in ways that make them more innovative? Let me show you another example of a network visualization that we put together to kind of illustrate this from a different perspective. Wrong one. This is a different sort of visualization. This is another dot, but this dot represents a study about patients with MS done with Beth Israel Deaconess Medical Center. The diameter of that circle represents 413 patients with MS whose samples, kind of blood samples and DNA samples, were taken from a common biobank repository. The green represents another study, so that's SUNY Upstate Medical University. They took from the same biobank. What that means is just at random, if you have these two kind of uncoordinated studies, but they're pulling from the same biobank, in the middle, there is that overlap of red and green. Those are two different studies. They weren't overtly organized, but there's 140 people with MS that have been studied from both organizations in two different dimensions. And now we can see the overlap of 3 studies. There's a small 4th study. We can bring in 5 studies. When this starts to get overwhelming, we can turn off the connectors and we can just look at the stacks of overlap. And the Accelerated Cure Project has really facilitated this by having a simple rule that says we'll give you physical material for studying MS. You just give us the data after you do your study. And then they came to us and they said, well, we have all these data now from all of these different organizations. We know that they've probably looked at the same patients and that there's a lot of power in that. How do we communicate that? How do we show that? And we came up with this tool. And this tool is also about connecting dots. If you use this tool to look at particular organizations that we've selected over on the left, sure enough, just due to the scale, some of the things that Dr. Barabazi was talking about, you will find that there are a small portion of patients that have been studied by Beth Israel Medical Center, GlycoMinds, Pfizer, SUNY University, Wellcome Trust. It's quite possible that, and there are cases where there's 10 studies, 12 studies, those study stacks are areas where we know more about those people with MS than anybody else with MS in the world. Now, why is that important to me, going back to the idea that it's not just about connecting the dots, it's about connecting the people? Why, anyone have any idea why I picked these 5 for this slide? These 5 organizations? What's that? Exactly. Exactly. It's not what they have in common, it's how different they are, right? There's academic, there's a medical center, small for-profit institution, huge pharma, university, trust. It's totally different. These are 5 organizations that would not necessarily collaborate together. They wouldn't think about writing a grant together. But yet, due to some infrastructure that's been created, they kind of already have collaborated together. They don't know it yet, because they haven't seen this overlap, right? And what if we could then click a button on this study stack, and this is what we're working on next, click a button, send an email to those principal investigators, and tell them, hey, you've all studied the same 140 people from 5 different angles. Maybe you should compare notes and see if there's something new to be had there. What if we could make a real physical collaboration out of what started as a serendipitous virtual collaboration? To me, that's the real exciting thing about the technology, the kind of network technology that's evolving. Let me show you another example of networks. I'm going to show you a little bit behind the scenes of how we build our visualizations at Exaptive. So we developed this environment that is an environment in which we can bring in different kind of Lego blocks over here on the left, Lego blocks of code. See if I can figure out how to, oh, that was the wrong button. Oh, maybe this is the right button. There we go. So we bring in a Lego block of code. This is a text box. This is a PubMed data object. So we're bringing in a data source. This is a word cloud. Oh, that's the PubMed. This is a word cloud. And we are going to build up an interface over here on the right. And as we bring in our different components, that's a progress indicator, we're going to wire them together. So this is called data flow programming. And we wire them together, and what that does is it produces an application here that allows us to search PubMed and get back in a word cloud of results. So what I think is interesting about this is that this is another example of a network, right? Let's look at this. This is a computer program, but this computer program is made up of a few discrete different libraries. There's a data library, there's a UI library. We could make this more complicated. We could bring in natural language processing, algorithmic libraries. The point I want to make is that just like in the other networks I've shown, there's people behind the points, behind the nodes. Every one of these libraries was written by somebody. Every one of those libraries is used by a particular person. And what if we could unlock that sort of network? So one of the things we built into our platform at Exaptive was exactly this idea that by capturing the metadata, the network of the way people use programming libraries, we could create something that we call a cognitive network. So when somebody adds a component for connecting to a Transmart database, for example, we can build a network that says, oh, that frequently gets used by Magali Haas, and she looks at it using parallel coordinates. And that's also, that technique is also used by Eric Newman. And then this becomes a hypergraph. We can go out, we can say, well, what else is Eric Newman using? He's using an overlap diagram. Both of those were made by Stephen Ara. He's also using a bunch of different data sources. So the point I'm trying to get at here is that we have data and we have metadata, the data about data. And by harnessing the metadata that lets us get one step further out, meaning getting from the use case to the people involved, I think we open up a really exciting new potential for using technology to connect people together, not based on what they say, but based on what they do and how they're doing it. So we call this the cognitive network, and this is an example of a much more complicated computer program. This network builds this user interface over here. What's interesting is as we start building far more complex data analysis consoles in our Exaptive platform, we start seeing scale-free network dynamics over in our data flow environment. And we also begin to see scale-free network dynamics in the cognitive network of the sorts of components that are frequently used. This is why I think this is exceptionally important, because there's another type of network that we have to talk about, and I think that is ideas. It is increasingly gaining acceptance that ideas are a network. And this was something that was published in the New York Times just a few months ago called The End of Genius. We like the mythology of the lone genius that has a great idea in a sudden flash of insight. But it's not true. It makes a great story, but it's actually not how insight happens. Insight happens much in the way that Dr. Barabazi was talking about the sudden coherence of a network made up of a lot of individual parts. Somebody who's working on an idea hears different bits and pieces, and the ones that seem the most relevant begin to combine together, and at some point there is a critical mass, and that is the aha moment. But it's very much not the lone inventor's aha moment. It is the network's aha moment, and the lone inventor becomes the conduit to explain it once it's happened to him. And what's exciting to me when I think about that is I then look at these sorts of networks, thinking about the people behind them, and I don't see a network of multiple sclerosis studies. I see a network of ideas that have happened, those studies, and I see a network of potential ideas that have not yet happened. When I look at our programming environment, I see a network of ideas an idea that has been implemented, and I see a network of ideas that have not yet been realized. And when I look at this kind of wonderfully complex integrative medicine community, I see a network of ideas and a network of unrealized ideas. And what we're trying to do with our company, and what I'm very passionate about, is how do you realize those unrealized ideas? And just like Dr. Barabazi was saying, well, the first step in being able to fix things, to be able to fix the communication problem in the company, is understanding how it works, understanding how networks work. Then you can start to make some suggestions about policy. I think if what we want to do is unlock new ideas, we have to kind of understand how they work. And I'm going to propose that an interesting word to understand how ideas work is this word exaptation. I've become so obsessed with this word, I named my company after it. Even though it's hard to pronounce and everybody stumbles over it for a little while. I'm curious, anybody know the word exaptation? Yeah, I've already told him. Okay, so in the early 80s, Stephen Jay Gould, evolutionary biologist, published a paper. He called it Exaptation, the Need for a New Word in Science. He said, we're all excited about evolution and adaptation, but if you look at enough evolutionary processes, you see something that happens that's not just adaptation. It's something different. We don't have a word for it, and we need one. It's when something that evolves due to one set of constraints gets serendipitously co-opted for something completely different and ends up thriving there. It turns out that feathers evolved because they kept animals warm, and then they got serendipitously co-opted for flight because if you trap enough air to stay warm, you might flutter off a cliff and not die when a predator chases you off it. And I think that this isn't just a biological phenomenon. I think this is a cognitive phenomenon, that a lot of the aha moments are mental exaptations when we realize something that we thought only applied in one particular area can often with that kind of flash of insight, we realize, because of the network of ideas we've surrounded ourselves in, we now see that it can apply in some completely different areas. And I'm not just making this up. This happens all the time, right? So Gutenberg, most people know that Gutenberg invented the printing press. Not everybody knows that he went to a vineyard before he did so. If you actually look at the two mechanical devices, a wine press and a printing press, they're amazingly similar because one inspired the other. If we take a modern day example, this is by Jonathan Cachet, who's a neuroscientist postdoc. This is your zebrafish. This is your zebrafish on drugs. If you are trying to make a machine algorithm that figures out what drug your zebrafish took based on how erratically it's swimming, it turns out that you can exact a machine algorithm from the weather that looks at the way that a hurricane moves and figures out something about the storm based on its movement. Here's an example close to home. Do any of you guys know about the Astronomical Medical Project at Harvard? Okay. It's an astronomer and a neurologist met at a cocktail party. The astronomer, it sounds like a joke, it's true. The neurologist said, "What's hard about astronomy?" The astronomer said, "We're trying to infer a 3D reality from a bunch of 2D radio telescope images." And the neurologist said, "Oh, wow, that's like an MRI. You know, it was really hard to read MRIs from a bunch of 2D slices until we got computer software that stitched it all together into a 3D model." And the astronomer said, "You have software that stitches it all together into a 3D model?" And so they plugged the radio telescope imagery into the MRI software, and they built 3D models, and they published a bunch of papers. So this at one level is extremely exciting, but I actually think it's also kind of tragic. I think it's tragic because this relied on two smart people meeting at a cocktail party and having a conversation in which they were able to talk at a high enough level of abstraction that they understood each other, and that's extremely rare. So my point is that when we're trying to facilitate innovation, I think serendipity is highly overrated. I love it, and it's romantic and it's great, but can't we use technology to stack the odds in our favor of innovation and insight? And civil engineers have created a machine that manufactures serendipity. You guys know what it is? You gotta give me 1 extra minute on my talk because I'm soliciting audience participation. It's cities. Cities manufacture serendipity because they produce something that Jane Jacobs called productive friction. We get a bunch of us all in close proximity, and we have to wait in line for our mocha latte, and maybe if we aren't completely caffeine deprived, we'll have a conversation with the other person that's waiting for their mocha latte, and we'll find out that that person in Cambridge is highly overeducated and has something interesting to tell us about our own project. That's how cities work. And software engineers build something different. They build social networks. And I was very excited when I watched the rise of social networks because I said social networks are kind of like virtual cities. You can get 500 million to 1 billion people all packed into a little fiber optic cable. That's a city, the population density of which doesn't exist on Earth. That's going to produce lots and lots of ideas. But it doesn't actually. It kind of produces a lot of cat videos and a lot of advertising. And what I realized is that, and I think that this, I would say, I think this is something we need to become more nuanced in the way we talk about it. Whenever we bring people together in these networks, we tend to call them social networks. But I would say that social networks are not the same as work networks, that people do not listen to hunky surfer Jensen Taylor on Google Plus for the same reason that they listen to Steve Jobs. And that actually we don't need more social networks. What we need are cognitive networks. And this goes back to something that Elaine has talked about and Dr. Barabazi talked about, which is communities versus networks. Jane Jacobs said the definition of a city is everybody is a stranger. That's very different. That's very different than small towns where everybody knows your name and knows your business. And we need cognitive, in that way, Facebook and Twitter, these are not virtual cities, as I first thought. I think they're actually a lot more like virtual suburbs. What we need to create is we need to create a virtual city where people can come in and they can think hard about difficult problems and they can get tired, and then they can go back to their virtual suburbs and tweet and share pictures about their day. So We need cognitive networks that stack the odds in our favor of these acceptations that might lead to insight. And so I'll end by kind of leaving the ball in your court along those lines, which is we've created this network map. And in a few minutes, after you hear some interesting ideas, you're going to get to go for a coffee break. And I encourage you to use this map and find maybe not somebody that's one hop out from you. You already know that person. And maybe not even the person that's two hops out who's the hub, because everybody knows the hubs, but go another hop out. Find the person that you might not normally talk to at this conference and have a conversation that perhaps might lead to some sort of acceptation. I think that is what we have to do as people, and as a technologist, I feel like that's where we have to push the technology. And I think that what Helene has put together today is just an amazing step towards trying to do that together, because today you all are the people in the dots. So I hope you'll make the most of it. Thank you very much.
Well, welcome everybody. I'm Peter Wayne, and I serve as the Director of Research for the Osher Center for Integrative Medicine. And I have the privilege today of facilitating this next segment of the forum, which we're calling the Poster Synopsis Medley. But before doing that, I just wanted to take a moment to say thank you all for your attendance. This is really remarkable. It's really incredible, and I know you're all busy, and thanks for taking time out of your busy days to join us for this important event. I also wanted to express my gratitude to all the collaborating centers for their participation in helping organizing this, and of course to our sponsors. So the idea for this medley grew out of our broader network vision, which includes not only catalyzing lateral collaborations and interdisciplinary work, but also vertical. We wanted to bring together the junior scientists and give them a voice in this event. And I think these are the new nodes that Dr. Barabasi and Dave King have talked about that are going to come into our network and really spark hubs of new ideas. So towards that end, we had 38 poster submissions, and a small committee picked 12 that we thought were both of very high quality, but also represented the diversity of ideas that are happening across this network of researchers. So in this very high wire act, each of the 12 presenters will be given strictly 1 minute to introduce themselves, to summarize their work, and to entice you to visit their posters so they can share some more ideas about them with you. To ensure that we stay on time, please reserve all your clapping and whistling and cheering to the very end of this segment. So without further delay, I'm going to set up the slides, which are actually on a timer. So this really is a high wire act, and let our presenters share their ideas.
Should I do anything?
Can you guys switch? You're on.
It's counting, but it's not showing.
Houston? Thanks, Matt. Or was it just the connection? So we're going to start all over again. You're on. Oh, never mind.
Okay. So a growing number of studies show measurable anatomical differences between the brains of people who practice meditation and those who don't. Even after only 8 weeks of training in mindfulness meditation, changes have been reported in the brain of people who have never meditated before. However, there exist many different types of meditation training, and they may impact the brain differently. So here we conducted a randomized control trial to investigate changes in brain structure after 2 different types of meditation training compared to a third control group. We found that participants who had meditated more during the 8-week training showed a larger increase in size in the hippocampus, an important area for stress regulation, which suggests that meditation training may revert the reduction in volume in the hippocampus found in PTSD, major depression, and other conditions. In addition, participants in the compassion meditation training showed increased cortical thickness in the dorsomedial prefrontal cortex, an area activated during empathy. So overall, our results suggest that different types of meditation training may promote neuroplasticity in different brain networks.
Hi, my name is Bethany Butzer. I'm a postdoctoral research fellow at Brigham and Women's Hospital, Harvard Medical School. My poster is titled Acute Effects of School-Based Yoga on Student Mood, and my collaborators were Satbir Khalsa and Josh Felver. In terms of background, there's research suggesting that adolescents and children experience high levels of stress and psychiatric disorders. And there's also research suggesting that school-based yoga might help with these factors. But no studies to date have examined the acute effects of participating in a single yoga class. So the purpose of the study was to compare the immediate effects of participating in a single yoga class versus a single physical education class on student mood. We had 9th and 10th grade students who completed self-report questionnaires of mood immediately before and after a single yoga class, and then immediately before and after a single phys ed class 1 week later. And we found that yoga provided unique benefits above and beyond physical education on some, but not all, of the mood subscales that we measured. So if you'd like to learn more, you can come and visit me at poster number 3.
Hi, I'm Claudia Fitzgerald, and I'm a research fellow at Harvard School of Public Health. We know from previous study that unhealthy behaviors such as physical inactivity can be related to distress later on. But surprisingly, we don't know if anxiety and depression can affect the likelihood of adopting a healthy lifestyle over time. So we followed 45,000 women over 15 years, and we found that regardless of the initial level of their health behaviors, anxiety and depression was related and had a significant impact on lifestyle later on. We also found that distressed women were 80% less likely to engage in a healthy lifestyle later on, and 20% less likely to maintain their healthy lifestyle if they had one initially. Anxiety has also a stronger effect in older women, while depression has a stronger effect in younger women. So distress may be an important target of prevention for chronic diseases. Thanks.
Hi, my name is Brian Gao. I'm an engineer and I work at the Osher Center. The project I'm presenting on comes from research led by Dr. Peter Wayne, with collaboration from many researchers and institutions in the Harvard Medical School system. Maintaining balance is increasingly appreciated as a complex task with inputs from many different systems. Our study investigated the long and short-term Tai Chi training on postural control and physical function. Specifically, we explore whether newer complexity-based measures of sway that presumably capture moment-to-moment variation and coupling between systems offer additional insights into Tai Chi's effect on the balance, on postural control. Above and beyond what typically is used to study postural control, like sway speed and area. If you come by poster 16, you'll see what I think are pretty interesting results. Thank you.
Hi, everybody. My name is Ronald Garcia from the Martino Center for Biomedical Imaging. Vagus nerve stimulation is an invasive technique that has been approved. Sorry. Okay. Vagus nerve stimulation is an invasive technique that has been approved for the treatment of some cases of clinical depression and also epilepsy. This method has also shown some potential applications for the treatment of chronic pain. However, a high incidence of surgical complications and other adverse events limit its applicability. In the last 10 years, a new technique named transcutaneous vagus nerve stimulation was developed. This technique consists on non-invasive stimulation of the vagus nerve at the auricular branch of the vagus nerve. And results from our laboratory show that the synchronization of this electrical stimulation with respiration could enhance the analgesic effects of this therapy. Because of that, we performed a functional MRI study in migraine patients and evaluated the brainstem response to this technique. Thanks.
Hi, I'm Paula Gardner, and I am the Assistant Director of the Program for Integrative Medicine and Healthcare Disparities. So if you come by poster 13, you can hear more about our Program for Integrative Medicine and Healthcare Disparities. And what we're going to be talking about today is our group visit model, where we have combined 3 paradigms: the mindfulness-based stress reduction, plus integrative techniques such as acupressure and massage, and a medical group visit. And our poster is talking about our qualitative data. There are basically 4 findings from our qualitative data that we wanted to share with you, which was an increase in nutrition and eating habits improvement. Also, that we found that our patients were more aware of the changes in measures in health, such as awareness of their blood pressure and weight, that they were incorporating more physical activity into their life, and also that there was a feeling of not being alone and having less depression because they were being part of a group.
I'll take the extra 10 seconds. I'm Adam Gonzalez. I'm an assistant professor of psychiatry at Stony Brook University. So the study that I'm going to talk about is an uncontrolled clinical effectiveness study evaluating the Relaxation Response Resiliency Program, also known as the 3RP. This is a comprehensive mind-body program that was developed at the Benson Henry Institute, specifically and systematically designed to target chronic stress and promote resilience. So this study evaluated 222 patients who were presented to the Benson Henry Institute for treatment. We further categorized the patients into 3 clinical groups based on their primary health concerns, so mental, physical, and comorbid conditions. We were particularly interested in the comorbid conditions since that population tends to be high drivers of healthcare costs, have worse disease states, and poor psychosocial functioning. So in these 2 tables, we present Cohen's d effect sizes, pre- and post-treatment changes in mental health and also physical health symptoms. You'll see that across all 3 groups. There were moderate to large effect sizes for the mental health symptoms in all the SCL90 domains, and also differences in an array of physical health symptoms. Thank you.
So hi everyone, my name is Ren Feng. It's my honor to be here today to present the study of Tai Chi treatment for depression among Chinese American patients. The study was primarily conducted by the Depression Clinical Research Center at Mass General Hospital. Regarding there are significant health disparities for mental health care among ethnic minorities, especially for Asian Americans, due to their language barriers and the strong cultural stigma towards mental health disorders such as depression. So we wanted to develop and examine culturally sensitive programs and mental health interventions for this population. Our study finds that Tai Chi intervention was feasible and safe, and it actually helped improve the treatment outcomes of Chinese patients. If you want to know more about our study, please visit my poster, which is number 11. Thank you very much.
Hi, my name is David Vago. I'm an instructor in psychiatry at Brigham. So our study really looked at 2 fundamental questions about meditation. One was, can we explore the relationship between the spectrum of meditation experience and bold activation patterns during an open monitoring meditation? And number 2, we know that when you meditate, you have fluctuations between levels of clarity and levels of mind wandering. So we looked at peak states of clarity during the meditation state. And so here's just a little tidbit. We saw some caudate activity across the meditators, and then there was a really dramatic increase in frontal polar activation that correlated with meditation expertise and a modulation of limbic areas that also correlated with meditation expertise. So come check it out, poster number 35, and I'll tell you more about what we found.
Hi, I'm Lisbeth Berrueta. I work with Dr. Ellen Lanscheffing at the Connective Tissue Lab, Osher Center for Integrative Medicine, Brigham and Women's Hospital. We are interested in manual and movement-based therapies such as yoga. We focus on connective tissue physiology and pathology, and its main component, the fibroblasts. And we are intrigued about the molecular basis of fibroblast response to stretching. We have found very exciting evidence that suggests that this response is followed by the activation of an ancestrally conserved signaling cascade involved in controlling cell size and differentiation. We believe this is a homeostatic mechanism orchestrated by the cell in order to preserve connective tissue plasticity. We invite you to visit our poster number 1 to discuss further this result. Thank you.
Hello, my name is McKenna Longacre, and I'm a second-year med student here at HMS, and I'm so honored by this opportunity to share this important information, which is part of an ongoing collaboration at Boston Medical Center's CAM clinic for refugees. As some of you may be aware, BMC is the major point of care for Boston's diverse refugee community, and this inspired us to offer free complementary and alternative medicine treatments to refugees. What we found in this particular study is that when given access to alternative medicine, including acupuncture, not only did our patients experience less pain, but also their need for primary care services significantly decreased. What we saw was a $691 per patient per month decrease in expenditures just relating to primary care services. If you start to think of all the other specialty services that are involved with the treatment of chronic pain, such as orthopedics, surgery, radiology, you can appreciate how important this impact may be. So with this, CAM may not only provide better tools to care for vulnerable populations, but may also decrease the profound cost of caring for vulnerable patients. Thank you.
Hi, I'm Catherine Hall. Pharmacogenomics has expanded our understanding of cardiovascular disease pathophysiology and raised the possibility of truly personalized medicine. COMT is an enzyme that degrades catecholamines and is emerging as an important hub in network medicine with links to both cardiovascular disease and drug metabolism. We recently demonstrated that in the Women's Health Study, a large randomized control study of vitamin E for the prevention of cardiovascular disease in 23,000 women, COMT is associated with the outcomes. As you can see here, in women homozygous for the high-activity COMT enzyme, at the bottom in the dotted black line, they had the lowest incidence of cardiovascular disease. Compared to the women with the low-activity version of the enzyme, they have the highest, which is a solid black line at the top of the graph. When the women with the low-activity enzyme took vitamin E, they had tremendously lower rates of cardiovascular disease, as seen in the solid red line, whereas women who had previously been protected from cardiovascular disease had an increase in rates. This is important for personalized medicine and pharmacogenetics. Thank you.
Well, that was fabulous. Thank you all. Photo opportunity? So I have a couple of announcements. So we're going to now move to a 30-minute coffee break. And we encourage you to use this time to visit the posters and have further discussions with the presenters and to meet new people in the network you may not have met before. But some other housekeeping items. We need all the center presenters as well as any moderators and award presenters to come up front here, and we're going to do a group photo as well in the next few minutes. So please come back to this site if you're in that group. And finally, if there are any poster judges who have not handed in their score sheets, please bring those to us as well. All right. Thank you very much and enjoy your break.